Okay, everybody, next up, we have Niklas Gustavsson, who will be talking to you about a data-driven study of a large-scale micro-component architecture. Give him a warm round of applause. And then later, there was whooping. Oh, I like that. Later, rate him on the app and ask him questions on the Slido. Niklas, all yours.
Perfect. Thank you for the introduction. Yeah, so as mentioned, I work at Spotify. I'm Niklas. I'm going to try to kill you by graphs today. I'm going to show you a ton of different data points for how sort of Spotify works beneath the surface. Hopefully, some of you use Spotify and enjoy it or hate it, whatever. We're going to be focusing on how it actually works today. So we run what could be called a microservice architecture. It happens that we've sort of done that in a way that predates the term itself, but it really is sort of following the same set of principles. We didn't do this because we were exceptionally smart back 15 years ago, but rather than we did this bet on this like Unix philosophy of each thing should do one thing and do it well, and we really try to replicate that for how we think and build our services. But as it happens, and we'll talk more about this, we do this for all types of components. We really found that this pattern works, independent if it's backend services, data pipelines, mobile components, whatnot. Same set of principles. And some of those principles are around ownership. So Spotify has around, I think this is on the slide later, but around 600 something what we call squads, teams, or engineering teams that build things. They have full ownership of their components. They decide which components they need, how they design them, they build them, they operate them, they sunset them at some point in the future. And that then funnels into something we call systems. These are logical groupings of software components. You can imagine our playlist system, which I'll show in a slide or two, is one of those systems. Typically, a team owns one or more of those types of systems. Within a system, there are components. This is mostly what we're going to be talking about today. Components is an individual backend service, an individual website, whatever it might be. And these components are then deployed in many, many instances in our runtime. We're not going to talk about that at all today. And components has dependencies on each other. So if you saw Sam's talk this morning, he talked about the arrows as being the most important part, and we're actually going to be spending most of the time on the dependencies today as well. So he might have been right. So I just want to show you this diagram to sort of connect things together and make sure that we sort of understand what the most important thing for today's talk is going to be, this component layer. So let's take a look at a practical example of this, and I mentioned the playlist system. So this is a highly simplified illustration of the playlist system, and also from a few years ago, actually. But it sort of shows you how we have this vertical stack. It's, in this case, this is a few years into its existence, and it has become split into these two different systems because we actually ended up splitting the team. So we had one team providing the sort of backend API and client-side APIs for it, and then one team that was executing on the user experience. So we ended up splitting it. But you can see how these things connect together. Each of the blue boxes in here represents a component of different sorts, and the outlined ones are systems. Hopefully that makes sense. So the focus of the talk today is really going to be a case study of one sort of large-scale microcomponent architecture. I'm not going to claim that we're doing everything right at Spotify or that we have all the answers, so this is just an example of what one of these might look like. I wouldn't recommend you to go back home and sort of try to replicate whatever we've done, but you can maybe get some learnings of the mistakes and, in some cases, good things we've done. And importantly for this talk, we're going to be looking at this from a data-driven perspective. So we're really going to look at the type of data that we can extract from our architecture and what conclusions we can draw from that. So let's talk a little bit about how we do that in practice. So we take a lot of sources. That might be our source code from our Git. It might be everything that we have in Backstage, which is our software catalog that we use. It's our org structure. It's a ton of these like declarative sources. We also have a lot of instrumentation in our runtime. So whenever a build runs in our CI environment, we collect a lot of information about that. Whenever we deploy something, all the pods that run in Kubernetes, we snapshot and dump into our data sets. And we do this across most or all of our infrastructure. All of this then gets collected, in our case, into BigQuery, which is this tool in Google Cloud that enables us to do ad hoc analysis. And an example, this is somewhat simplified, but an example might be of a query that we can run, can look something like this. In this case, we're looking at how many production data pipelines does a squad own. And we'll actually come back to the statistic in a second. So everything you're going to see today in terms of the data and graphs I'm going to share is based on queries basically looking like this. So let's look at what our components actually look like in practice. And again, reminded, this is the services, the data pipelines, mobile components. In total, we have 10,000 or slightly north of 10,000 production components. So that's like distinct, unique software components that we deploy and manage. Each of those are, just to give you a sort of order of magnitude sense of their size and complexity. Lines of code is maybe not the best metric, but at least it gives you some sort of understanding. You can see that on average they're around 3K lines of code. The exception is our mobile code base, and that's a bit of a side effect of how we do dependency injection and whatnot on mobile. So you can actually sort of ignore that statistics. It's more due to our infrastructure than the actual code that our developers work with. So if you look at a more sort of representative mobile components, it's roughly the same size. So that means as a developer, when you're working on one of these components, those are the sort of 3,000 lines of code that you need to know and sort of keep in your mind as you're working on it, and you can ignore all the other code that we have. I mentioned that we have a pretty strong notion of ownership. So every component is owned by a squad and only one squad. So that's very important to us because a lot of the run incidents or many other aspects, we need to be able to know which is the owner for this particular component. And I mentioned we have a little bit north of 600 squads, and on average they own around 6 components. Now, if you go back, the folks who are quick at maths can realize that 6 times 650 doesn't become 10,000. So in reality, as this graph shows, there's actually quite a skew when it comes to the number of components that squad owns, and there are some squads that owns hundreds of components. That is typically because they have some sort of infrastructure where they automatically generate new components, and each component is relatively cheap for them to own. So you can see that there's a long tail of the number of components that squads own. So one of the reasons why we have continued to build on this notion of having smallish components and having this strong notion of ownership is that we want to enable our teams to work fairly independently. When you own a service and you decide when you deploy that or what changes you make to it, you can work independent of all the other 649 squads. And a way to measure if we've been successful with that is to see, have we been able to keep up the number of deployments that we do as we've grown as a company? So again, each squad is able to decide whenever they want to deploy. It's up to them to make that decision. But we, of course, we value shipping very frequently whenever possible. So we have been able to see that the number of deployments has continued to scale linearly with the number of developers that we have. So in that sense, we think our architecture has been successful. And at the moment, we're at around 2,600 deployments per day, and that keeps growing, as you can see. There's also, as you can see in this graph, there's whatever that color is, purple line, which is the deployments that are due to a change made by a human. And then there's the gray line, which is deployments that are due to change made by some sort of automation. And as you can see, there's been quite a steep increase in those bot changes lately, and that's due to an effort that we call fleet management, where we're improving how we automate our software. I'm not going to talk more about that today, but if you're interested, there's a blog post series that we just published on our engineering blogs, and you can go read about what that thing is. But overall, this has shown us that we think this fundamental principle of smallish components owned by a team seems to enable us to scale up as a company, which has been a positive signal for us. Next up, and now it's going to get a bit more interesting and maybe a bit more involved. Hopefully I don't lose you, but we'll talk a little bit about dependencies. So again, this is where one component depends on another component. Might be a backend service making gRPC calls to another backend service, or having an event dependency on another backend service. Might also be a data set that relies on some data from some other data sets in order to be produced. Or a mobile component calling into another mobile component. Or even, but we're not going to talk about that today, for example, a mobile component calling into a backend service. Today we're only going to look at sort of dependencies within each of the types of components that we have. And that's due to limitations in our instrumentation at the moment. We don't actually know much about what those other dependencies look like. That's something we want to fix, but at the moment we don't have that instrumentation. The dependencies are collected through both these declarative sources that I mentioned. So some of those we can detect through our build system. Some of them we can detect through configuration, like we have a configuration for which services that are exposed in our edge infrastructure towards our clients. All of that is declarative, and we can just ingest that. There's also a bunch of these that we collect through runtime, so we actually have instrumentation of, again, like what we have tracing, we have other ways of detecting calls between services or lineage between data endpoints or data sets and whatnot. So like all of that is collected and consolidated into a single data source. All right, and again, reminder, going back to this picture, we're discussing these lines between components here. And to give you a sense of the sort of size and complexity, this is what the dependency graph for our production backend services looks like. In this graph, every circle is a unique backend service. So somewhere in there are those playlist services that I showed before, for example. I have no idea which one is the playlist service, but one of them is one of the larger ones because they're basically sized by how central they are in this dependency graph. And each of the edges, the lines between the nodes, is a dependency. So a service calling another service. And maybe you can get a sense of the sort of complexity here, and that there's a fair amount of dependencies in our graph. This is just generated in a way that sort of optimizes this graph. It doesn't show any layering or things like that in our backend architecture, but just to get a sense of the complexity again. So now that we have this dependency graph of all our components, we can put that into all the types of graph algorithms or network algorithms that are out there, and we can actually start using that as a way to derive metrics around our architecture. So one of those is centrality. This basically speaks to how many incoming and outgoing dependencies does a particular node have. In this weird-looking graph, this actually shows the distribution of that for our services again. And when you see a graph like this, a good idea is typically to plot this in a log-log way instead. So make both of the axes log scale. And if you do that, it looks like this. It's sort of linear if you're willing to squint a bit. And that means that we think that this network is what is called a scale-free network. You can go read about that. It's actually good for this audience. I think scale-free networks was actually largely researched on by Hungarian scientists. Anyhow, with this, we can make some predictions about how our network is going to behave. And in particular, when it comes to these types of networks, you have something that is called preferential attachments. So that means as we add more services, we should expect that we will continue to add more and more dependencies towards a few central services. And this is very much what we're seeing. So we have some of those. We can actually go back to that graph a few slides back. So you can see these like very big circles in the middle. Those are some of our very important or like central services that a lot of other services tend to use. And those are our core things like playlists that I mentioned that we looked at before, or our track and podcast metadata, for example, is something that a lot of other services use, and they will tend to grow in centrality. So that means from a operational perspective, we can now know that those are the types of services where we need to spend more time in terms of having good on-call practices or good tech health and things like that, because an incident with those services is going to be very impactful for us. If one of those big nodes is unavailable, there's going to be a lot of sort of Spotify user experience that is impacted. We can also look at these dependencies, and we can see if they are related to how our developers interact within the company. And I think this is going to be a challenging graph to read. Maybe it's okay. So the graph on the, whatever that is, left-hand side, your left hand, that shows a heat map. So you can imagine on the y-axis and the x-axis, we have all our squads, all our delivery teams. And the intensity of the color shows how many dependencies software dependencies do they have to each other. So the more a squad is calling into some other squad's services or has a dependency on their mobile APIs or on their data sets, the more color you're going to get in that heat map. On the right-hand side, we have the same thing, same squads on the X and Y axis, but instead we're showing the number of pull requests that they send to each other. This is over the last few months or so. And as you can imagine, when we look at the dependencies, you can see this clear diagonal going through the graph. And this is a sign that, as you can imagine, typically you have a lot of dependencies on your own software. So if you're the team that owns the playlist service, the playlist system, you have a bunch of services within that, and they're going to have dependencies on each other. So this is a sort of good thing, and we'll talk more about this in a few slides. You can see these horizontal lines, which are really sort of our platform teams. So these are teams that offers APIs that a lot of other teams use. And you can see we also have some of these vertical lines, which are actually a different set of platform teams. So we can start identifying different types of teams by looking at this data. And you can sort of see the same when you look at PRs. So again, you have that strong diagonal. Again, expected. Most PRs will be sort of sent between your peers in your team. But you also send PRs to other teams. We use like all the source code for Spotify is available for all engineers, and you can send a PR to some other team if there's some change you want to make. So you will see, again, some of those other hotspots popping up. But what's interesting for the purpose of this talk is that there's a strong correlation between these two. So the teams, and this is maybe not surprising and might be intuitive, but the teams that has strong dependencies, like have a lot of dependencies on each other in terms of their software, will also need to do a lot of collaboration. And one of the things that this can tell us is that having these dependencies are fairly expensive, like it will require a lot of future collaboration. So that means that we will want to optimize our organization around sort of optimizing around these dependencies. And we'll look at that in a few seconds. So with that, let's look at two examples of how we can use this type of data to guide how we make changes to our software and to our architecture. So the first one is an example from our mobile apps. So we have two main apps one for Android, one for iOS, unsurprisingly, and they have grown very much over the last few years in terms of the code base. And this becomes, as you can imagine, a challenge when it comes to our build times, both local build times when the developer is working locally and for our CI builds. And I think this graph, the top graph doesn't actually have any y-axis, but the spoiler alert is that we have millions of lines of code in our mobile apps. So building this becomes an extremely expensive operation if we're not smart about it. And it did. So our build times were horrendous a few years back. Typical CI build time would be north of an hour. Building locally was super challenging because of this problem. And we can look at this from again, from a dependency graph point of view. So if we look at this was the typical case. We have some sort of, each circle in this diagram shows a component, some library, some view component or whatever in our mobile apps. And we can see this, the filled circle in the middle, that's some sort of library that we have in the app. Doesn't matter which one. But the point is that the API for that and the implementation of that sat in the same component. And this means from a CI point of view that if we make a change to this component, some random transitive dependency of the central one, we will need to rebuild and run the tests for this entire graph of other components. And this is the reason why if I'm a developer, I'm working on a component and I'm making a change to it, I have to rebuild a large share of this like millions lines of code base, becoming very slow. And this is nothing new. Like, we've all heard about dependency inversion for years and years and years, and this is really what we need to do here as well. We need to split these two things. So again, from like a software design perspective, there's nothing new or spectacular here. But it becomes interesting when you need to do this in a code base with millions of lines of code and thousands of these components. Like, where do you even start? So what we did was to apply graph analysis to this. And essentially what we did was that we looked for where do we have the longest dependency chains in our code base. And it turns out that we had dependency chains of like more than 30 nodes or 30 modules. So on a straight line, so to speak, through that graph. So if you made a change to one of those sort of bottom dependencies, there would be an enormous amount of components that you had to rebuild. So what we did was essentially to stack rank, like, here's the order in which we need to do this work to start untangling this tree of dependencies. And as it turns out, this is sort of the best case scenario. I shouldn't claim that we did 10x across the board, but in a way to measure this, we actually introduced a component that was at the very bottom of the dependency tree. And we could measure, if we make a change to that, what's the build time? And by doing these changes over about a year, we could reduce the build time of that by 10x. So that, of course, then is pretty impactful for our engineers. And it's one way to use this type of data to inform what changes to, or what improvements to make and what ordering, how to make them. The other example, and this is going to be the last one, and I'm going to come back to what I was talking about before, like trying to optimize the organization around our architecture. I suspect most people are familiar with Conway's Law. It's this paper. If you haven't, you should go read it. It's not that long. And it basically says that for our part of the world, your software is going to reflect the way your organization looks. So if you have a certain sort of team structure, you're going to have software that is a one-to-one mapping to that. In our experience, this is sort of the law of nature. It's very, very hard to break away from this because just like how humans function. So typically what you try to do is something that is called the inverse Conway's maneuver. So rather than trying to break this law, you accept it and you try to organize your organization after how you want your architecture to work. I'm not claiming that we're doing this perfectly by any means, but like now we can start using this data that we have to start thinking about what our organization looks like. So there's this metric, again, if you're into graph theory, you probably know about this one. If not, you can go read about it. It's called modularity. It's the actual algorithm is more complicated than this, but an easy way of reasoning about it is think about like what's the ratio between dependencies that goes across teams versus dependencies that are within the team, within the team's boundary. And we can do this at team at any level. So we can do it at the squad level, or we can look at our larger organizations as well. It works in both, or at multiple levels of granularity. And basically what we want to achieve is to have a fairly high ratio of local dependencies over these cross-team dependencies. That means that our organization is well aligned with our software. We don't want it to be all internal dependencies. We actually want to reuse like platforms, internal platforms that we have. So there's a trade-off here, right? But at least we want to be within some guardrails. And we can look at what this actually looks like for Spotify. The actual number on the scale is not that important. I think in this case, it's more relevant to look at the sort of slope of the scale or the trend over a period of time. And I'm not going to debate if this is like good or bad. It's just like this is what it looks like for us. It would be interesting if you would do this with your architecture, and we can compare and contrast, but at least this is what it looks like for us. You can see at least it's going up, which is good. But again, hard to reason about exactly what it should be. You can also see that there are variations, like there's ups and downs in that graph. And those typically correspond to when we have made either organizational changes, like moved some software around, ownership around, that might, in some cases, improve our modularity, like that's good. And in some cases, it has actually reduced the modularity, which is less good, and we should probably be more proactive around when we're making those changes. Some of these changes, to be clear, is also due to changes in our instrumentation or architectural changes that we made, so it's not all due to these ownership or organizational changes. So with that, I'm going to try to summarize a little bit. So this is still very much work in progress. We're working on improving these metrics and the data collection and our insights that we can draw from it every day. We want to make these metrics useful and actionable to our teams. So we're internally building a bunch of dashboards, and we have a lot of these data sets that teams can use on their own if they want to go explore what their software looks like. And we have a bunch of teams that has been very successful in doing that. So like can inform them where to spend their time, or how to balance their time between paying off tech debt versus doing feature delivery, like those types of decisions. We can use this type of data to help inform. And we can also, when we sort of zoom out and we look at the whole company, we can make similar decisions. So I alluded to this fleet management work before, like that whole investment was informed by this type of data. So like we took a look at the complexity of the changes that our developers are doing, and by doing that, we could essentially figure out, like, do we have a positive ROI on making this investment or not? And yeah, so I can highly recommend trying to get some sort of instrumentation and similar thing in place for you. And with that, I'm gonna say thank you, and I'm gonna provoke some questions. So if you haven't put questions into slide already, or if you want to come up afterwards, I'm super curious about what I shared today. How does that compare to your architectures? And do you have ways to collect similar data or reasoning about your architecture and infrastructure in a more data-driven way? Would be very interested in hearing your experiences, because we're here to try to learn. Thank you.
Woo! Thank you, Niklas. We have questions and we have time. So we'll do both. Well, we'll do questions with the time. Gyuri, you go first because you used your name. What protection measures are there to ensure that if a component, it's moving around, that if a component dies, it has as little impact as possible on other components that inject that component?
That is an excellent question. I'm going to answer it primarily from the perspective of backend services, because that's where we have most sort of immediate impact when we have this type of outages. And there's not an easy answer to this, but we do a lot of work in our infrastructure to protect against these types of failures. A lot of it comes down to the sort of service-to-service communication and how that functions. Using patterns like circuit breakers, having a reasonable fallback or retry behaviors, things like that. But honestly, there's not a single sort of silver bullet here, and we do a lot of incremental improvements as we find new failure scenarios.
Thank you. Okay, next is Anonymous, who says, is Spotify based on event-driven architecture, or does it work based on a request/response model?
Maybe inspired by the talk this morning. It's 99% request response and sprinkles of more event-based communication between services. There's one major exception for this, and that is our event delivery infrastructure. So the way that we collect instrumentation from our clients or from our backend services, that is done in a highly event-driven way. And I think we process like north of 1 trillion events per day or something like that. So it's pretty crazy scale. There's a few years back, a blog post series on the architecture of that system that I highly recommend if you're into that type of thing.
Anonymous is back with another question. On the slide, you mentioned 2,600 deploys a day. Are they all prod deploys, or is it includes non-prod, open bracket staging or beta or similar close brackets as well?
Great question. Yeah, so they're all production deploys. In fact, I don't know if this is provocative or not, but we basically do not have a staging environment, and we don't believe in having a staging environment. Slightly more nuanced than that in practice. We do have some services that are deployed to staging environment, typically because they have some sort of partner integration or similar, where we need to do some additional verification. But by far, most of those deploys are straight to production. We rely very heavily on CI and having strong deployment practices to make that safe and productive. Great question, by the way. So if you found that controversial, come up afterwards and we can debate what the right strategy is.
Good job, Anonymous. Zoltan is here. Is there any protocol to decide if a dependency can be added, or is it up to the squads?
It is largely up to the squads. And I'm going to say that that's not just a good thing. We probably want to add a little bit more rigor to how we take on new dependencies and what dependencies we take on. So, but today it's, I don't know what a positive word would be, but it's autonomous maybe, it's a good word. Chaotic would be a different word. It's both of those. And again, I think this is an area where we need to improve a little bit. And I've spoken to some other companies around how they think about this. But we're also at a scale where like, it can't be that it needs to go to some single point to have it make that decision. So we need to figure out some way to do it distributed while getting that rigor built in.
Anonymous wants to know, what's the typical size of a squad?
Yeah, so they're your sort of normal Scrum-ish team. We mostly don't use Scrum, but so I would say it varies from maybe 4-ish up to 12-ish in that range typically. And when squads grow larger, they tend to go through some sort of cell division where they split into multiple squads. Smaller squads tend to not be very sustainable. Very hard to run we do, but it's quite rare, but it's hard to run like a 2-person squad, because when that person is, or one of the people are sick or on parental leave or whatever, it makes it challenging to run.
Peter has a question. What are the biggest architectural challenges you're currently facing, be it governance, technologies, etc.?
It's a really good question. I would say that the sort of time, so I would say we don't have any fundamental challenges. We did a few years ago. I showed a little bit of this like mobile work that we've done. And part of that story is that 4 or 5 years ago maybe, we had a largely monolithic well, two largely monolithic mobile apps. And as you heard me speak through here, we found that for us, having these small components with clear ownership really works in the way that we want to work. And having this large monolithic thing was not great from that perspective. So that, going back a few years, we had those types of fundamental challenges. I would say today we're not really faced with one of those existential crises, but we do want to become more effective and efficient in how we work. So again, the fleet management stuff I mentioned is an example of where we're trying to find ways of basically getting more work done with the folks that we have. So I would say that we're going to do more of those types of things over the next few years, and we're trying to figure out what those might be.
Thank you, Peter. Anonymous says, what tool are you using for the dependency visualizations?
So for that, yeah, it's not my slides anymore, sorry. So that like crazy dependency graph I showed is, it's all a graph with graph. So it's, if you're into GraphWiz, it's like a neato layout with just doing BigQuery to feed it with data. And I found that like there's a lot of more interactive tools out there, but they tend not to work well when you have 10,000 nodes put into them.
Are diagram approaches with tools like UML/C4 applicable at all to visualize architecture of components at Spotify?
Yeah, so I think Simon Brown is giving a talk here, as I should say nice things. C4, so we don't use UML mostly, I would say. Well, we do use sequence diagrams every now and then, but we did make a bit of a bet on C4 a few years ago, basically to have a shared language for how we visualize our software. It's not very useful to try to do at like the sort of try to visualize everything at the company. I don't think it's really intended for that either. But we do encourage our teams to use it when they model out their systems or their sort of nearest neighbor dependencies. And we also offer some tools to do that automatically. So within Backstage, which again is this like software catalog developer portal we have, you can go in and look at any system in there, and you can actually automatically get a C4 diagram for that based on this dependency data that we have.
Rezo wants to know, on the steep decreases in the lines of code plot, are you pruning the code base by eliminating a component or have a cross-components approach?
I'm not sure what the steep decrease is refers to, but we're doing a pretty shitty job when it comes to decommissioning components, to be honest. A metric I didn't show today that I track is something that we call our decommissioning rate. So we basically look at how many new components do we add over how many components do we decommission and remove. And that tends to be above 1 almost all the time. So like we keep adding more stuff, which of course then adds to our maintenance costs and so on. So we do want to become better and more structured around how we decommission our components, and with those components comes their source code, of course. There are also cases, and this I think is particularly true for our mobile apps, where we have sort of accidental duplication, where multiple teams might have implemented very similar things over and over again. So that is something that we're working on at the moment to start addressing.
Okay, and last one, and it's quite aggressive, this one. What exactly do you mean when talking about rebuild components? Is it about testing, compiling, running a pipeline, verifying it still works with the changes?
Yes, it's all of the above. When we do one of those rebuilds, I think this refers to that mobile basil example. So when we rebuild it in the naive way, the sort of before we started doing all this work, it was all of those. So it was compiling the code, it was running the unit tests, it was running the integration and system tests for it, and also generating the apps, which is expensive on its own. Now that we have a bit more of an intentional dependency graph, we can start doing build avoidance. So like we can figure out more smartly which components do we need to build and test and which do we not need to do that with. So that has also been, in addition to this dependency work that I showed here, being more clever about what we rebuild and test has also been an important component in running down our build times.
Fabulous, fantastic. Niklas, one round of applause for him, please.